Welcome to the deep dive. Today we are diving into a puzzle that has captivated mathematicians and logicians for, well, over a millennium.
Yeah, we're talking about the Knight's Tour.
That deceptively simple game of making a night visit every single square on a chessboard exactly once.
It really is ancient history meets the frontier of computer science. And this deep dive is based on a remarkable set of research notes and a recent lecture.
Right, detailing how these computational adventurers, led primarily by Donald Knuth, have tackled this puzzle. And not just to solve it, but to find its hidden laws and, its most elegant examples.
What's so great about the framing, I think, is how Knuth describes it. He calls the Knight's Tour this perfect collision of logic and artistry.
A right brain, left brain endeavor.
Exactly. The left brain is handling the rigorous logic of the Knight's L-shaped moves, all the constraints and the counting.
But the right brain sees the final path as a gorgeous design.
Yeah, you end up with these incredibly intricate, non-repeating patterns that just flow across the whole board.
And that aesthetic quality is why this problem has gone physical, right?
Yeah.
We saw in the notes the reference to the Case Western installation.
Oh yeah, where they render the paths as physical artwork. They almost look like Celtic knots.
And the challenge there was making sure the path correctly went over, under at every single intersection.
Which is just mathematical rigor applied to sculpture. I mean,
Yeah.
the path has to obey the rules of the tour and the laws of physics.
Okay, so let's unpack this whole journey. For you, the listener, our mission is to explore how modern computation took this 1,200-year-old puzzle and split it into three distinct, really ambitious adventures.
And these three projects, they really do represent the full spectrum of complexity analysis.
So what's the first one?
First, we have the census. This was all about depth, finding and classifying every single tour to uncover the absolute rarest properties.
Okay, depth, then what?
Second, blind counting. This one focused on sheer speed and scale, counting tours on massive, often non-square boards.
And the last one?
Finally, whirling. This was an exploration of new, sort of aesthetically pleasing constraints to push the boundaries of mathematical beauty.
That's a lot of ground to cover, all built on a single chess piece. Let's start by establishing the magnitude of the challenge. Where did this all begin?
The history is incredibly deep. I mean, it goes all the way back to Kashmir and Persia in the 800s.
Wow.
Yeah, and it was studied by Euler in the 1700s, who proved the tour was possible and often symmetrical.
So at first the question was just, can this even be done?
Exactly. But once it was clear that, yes, it could, the scope changed dramatically in the 1800s. People started finding tours everywhere, and the question shifted to,
How many are there?
precisely. And that's when the problem became truly paralyzing. In the 1850s, a French mathematician named Labourné tried to crowdsource the solution.
How'd that go?
Well, he estimated that just to write down the solutions they were finding would require more than 10,000 reams of paper.
10,000 reams. It's an impossibility in the pre-digital era.
Totally. It was like trying to count the stars with a pencil. But now, of course, we know the definitive answer, which serves as the baseline for everything that follows.
Okay, what's the big number?
Thanks to Brendan McKay's work in 1997, we know the exact number of closed Knight's tours on an 8x8 board is 13,267,364,410,532.
13 trillion tours.
13 trillion. And that huge number is the target that all of these counting methods have to hit to be considered correct.
And within that astronomical number, there was this question that sat unanswered for over a century. Tell us about General Parmentier's challenge.
This is a perfect example of how the aesthetic and the logical intersect. A Knight's move has one of four possible slopes, right? +2, +0.5, -0.5, or -2.
Okay.
Parmentier wondered if a perfectly balanced tour could exist, one that used exactly 16 moves of each of those four slopes.
16 times 4 is 64 moves, a full tour. And Huth said this problem just sat in his mind for decades.
Yep, which brings us to adventure one, the census. How did they finally get the answer?
Right, because the challenge of the census wasn't just counting the 13 trillion, but analyzing the properties of every single one of them.
Exactly. You can't brute force that. You have to be smart. You have to divide the entire universe of possibilities using symmetry and geometry.
Okay, so let's pause here because this is where the method gets really creative. How do you divide 13 trillion tours into manageable sections without missing a single one?
They used what they called the bunching method. The board is split into four symmetrical wedges that meet around the center, four squares.
So you're looking at how the path is sort of stitched together in the middle?
That's it.
Yeah.
It turns out there are 28 possible geometric connections, or wedges. So you have 28 to the power of 4 possibilities.
which is a lot. Over 600,000 cases.
Right. But by eliminating all the mirror images and rotations, they got that massive universe down to just 66,771 canonical bunches.
That's the key. So you turn one impossible task into over 66,000 smaller parallel tasks.
And they can all be solved independently. Kuth actually ran this census on his personal 8-core machine in about 66 hours.
Wow. And the first payoff was solving Parmentier's challenge from 1891.
It was.
So was this perfectly slope-balanced tour incredibly rare? I mean, given how long the question went unanswered?
No, and that's the amazing part. The census found that the total number is, well, it's over 103 trillion.
Wait, 103 trillion. That's more than the... Oh, wait, I see the 13 trillion was just for closed tours.
No, you're right to be confused. I misspoke. The number I should have given for the balanced tours is a subset of the total tours. Let me rephrase. Out of all the tours they counted, a surprisingly large number were slope balanced. About 1 in every 128.
So it's not rare at all.
Not at all. The problem wasn't its rarity, it was the sheer difficulty of counting and classifying everything.
Got it. But the census wasn't just about counting, it was about finding the extremes, the real outliers.
That's the real aesthetic gallery. For instance, they cataloged tours by their sharpest turns. The old record was 26 sharp turns in a single tour. The census found a new record,
Which was?
29.
And how common are those?
Vanishingly rare. Out of 13 trillion tours, only 136 of them achieved that maximum.
It also let them confirm things like the minimum number of right angles is 2 because 0 was proven impossible.
Right. And then there's the one Knuth called a rare gem, the perfectly obtuse tour.
What's that?
It's the one unique tour that has the minimum possible number of obtuse angles, which is 4. A single solution. The census allowed them to find and verify this specific, beautiful design.
And they applied this to chaos too, right? Finding the most and least chaotic tours based on path intersections.
Yes, the least chaotic tour has only 69 intersections. Only 5 are known. On the other end, the most chaotic has 126 intersections, and that tour is entirely unique.
Okay, so that brings us to the darkest tour census. This sounds like the most computationally demanding. It involves something called the winding number.
Right. The winding number is basically a way to measure the intricacy of the weave. Imagine you draw a line through the center of the board. The winding number counts how many times the path crosses it.
So a higher number means a more complex or darker pattern.
Exactly. And to analyze 13 trillion tours based on that specific metric, they needed serious computational muscle.
How much?
They had to use 832 cores across 26 separate machines, running for days. But that effort paid off. It isolated the single tour with the maximum winding number, a question Knuth had for decades.
That is depth. Okay, so let's pivot to adventure 2, blind counting. Here, the goal shifts from finding rare gems to just pure overwhelming speed.
And scale. The census method is perfect for a square 8x8 board, but it breaks down on rectangular boards, like an 8x12 or an 8x32.
So you need a new method. And they use dynamic programming, which tracks the frontier. What is that exactly?
Instead of calculating the whole path from the start, dynamic programming builds it one step at a time. The frontier is just the boundary between the squares you've visited and the ones you haven't. The algorithm only needs to know the state of that boundary.
So you're not wasting memory cracking every step from square one. You only care about where you can go next.
Precisely. It's a huge memory saver. And the speed gain is immediate. On the standard 8x8 board, this method confirms the 13.2 trillion count in under 3 hours.
From 66 hours down to 3, that's a huge leap. But the real adventure here was pushing this to the absolute limit on a massive 8x32 board.
This is where it becomes less computer science and more high-stakes operational thriller.
I love these stories. So the 8x32 problem required a ton of RAM.
A colossal amount. They started the job on a special high RAM machine named Rambo.
Rambo, built to survive. So what happened?
Rambo died. It had an uncorrectable memory error, a parity error, and the whole job was lost. So the team rewrites the entire program with robust backup and restart systems, and they move the whole operation to an even bigger machine.
Enter Trinity.
Trinity, a machine with 4 terabytes of RAM. The calculation is restarted, runs for days, it's getting close to the end, and then Trinity dies too. Just days before the lecture where the result was going to be presented.
You're kidding me. That's just incredible bad luck.
It was a photo finish. But because of those new backup systems, they were able to salvage the process, restart it one last time, and get the final result just 48 hours before the talk.
What was the number?
A staggering number. something like 1.38 times 10 to the power of a 134.
But the real point of pushing to that extreme scale wasn't just getting the number itself right, it's what the number revealed.
This is where it gets profound. The computation revealed an asymptotic formula, a hidden law of nature for the Knight's tour.
A law of nature.
They found that as the board gets longer, the number of tours on an 8xn board grows by a predictable, consistent factor. It's roughly c times 526.46 to the power of n.
So that constant, 526.46, that's the key. It tells you how much the number of tours multiplies every time you add another column.
And that means you don't have to run these massive error-prone calculations forever. You can now predict the number of tours on even larger boards with a high degree of confidence. You found simplicity inside the complexity.
That is phenomenal. Okay, let's shift to the final adventure, whirling. This brings us back to aesthetics, but with a new, very strict rule.
This adventure is all about creating mathematically beautiful tours using the concept of whirling. A whirling tour is defined by one rule. The Knight is always moving in a counterclockwise direction relative to the board's center.
It can never turn back on itself. It's always spiraling.
Exactly. This introduced the concept of coils, the number of times the path crosses the line running through the center. On an 8x8 board, the first whirling tours they found had 7 coils.
Which led to 2 unsolved questions for an NXN board.
Right. First, can a tour have n coils? And second, can it have the absolute minimum, n divided by 2 coils?
The N coil problem seems like it should be possible.
It's trickier than it sounds on small boards. The breakthrough came when Knuth's collaborator, Nikolai Bella, used a different approach called integer programming.
How does that work?
Instead of searching for a path, integer programming treats the board as a system of constraints. It basically forces the geometry to obey a set of hard rules.
So you're telling the computer, build me a shape that follows these exact rules, rather than just searching for one.
That's a great way to put it. And that method produced the first known example of a 12 by 12 tour with exactly 12 coils. It proved the n coil goal was achievable.
Okay, so that leaves the minimum coil question. N divided by 2. Did they find one?
They did. That was the final discovery. A magnificent 18 by 18 tour was found that had the absolute minimum of 9 coils.
18 divided by 2.
But what makes it truly spectacular is that this tour also has perfect 90-degree rotational symmetry.
That's the marriage of logic and beauty we started with.
Absolutely. Knuth described this final solution as looking just like a wonderful Christmas decoration. It's a perfect end to the adventures.
So stepping back, we've seen this incredible transformation. The census gave us depth, revealing rare gems. Blind counting gave us scale, uncovering fundamental growth laws. And whirling gave us new avenues for mathematical beauty.
It just drives home the point that mathematics isn't a closed book. Even in a simple system like a chessboard, pushing computation can uncover these real underlying principles. And those principles often govern immense beauty.
Now, this entire discussion has focused on two-dimensional boards, but our source material points out that the Knight's tour was famously extended into the third dimension.
That's the next frontier. If you take a 4x4x4 cube, you have 64 cells, same as a chessboard. The Knight's move is just extended into 3D.
And a few of those 3D tours are known.
A few are, yeah. Some with beautiful symmetries that wrap around the shape. But the big, unsolved computational challenge remains.
And that challenge is the question that awaits the next generation of adventurers.
What is the total number of closed Knight's tours on a 4x4x4 cube? No one knows. We have no idea if the answer is in the hundreds, the thousands, or the billions. That number is just waiting for the next high-stakes computation.